Okay, here we go. This is lesson 8 of energy and momentum. There's 3 examples that we're going to go over. They're going to be relatively quick, and this will be it. So we're going to look at larger problems now, connecting momentum and energy together and seeing what we can do with all of that. So together, these 2 concepts can be used to solve rather complex problems. So for example, we have a block hanging from the ceiling and we're going to shoot it with a gun, obviously, but bullet's going to hit the block, embed itself, and we want to know the height at which the block is going to rise. So with all of these kinds of problems, this is actually my second favorite lesson to teach. There's a lesson coming up here that's actually a lot of fun that involves this as well. But what we're going to do is we're going to start combining these particular concepts to look at how to approach this entire problem. So we need to first be able to break this thing up in a way that helps us identify what concepts to use where. So the first thing we've got here is a bullet embedding itself in a block. Now, this particular part of the problem is a collision, and so because it's a collision, we're using momentum. After the collision, this thing's going to move, and it's going to rise. Moving and rising is kinetic energy and potential energy, and so what we've got over here is the energy portion of the problem. So we want to figure out how to combine these things. So let's go. If we break this problem up like this, by looking at the collision first, we know momentum has to be conserved, so initial has to equal final. Initially, we've got 2 distinct objects. Finally, we've got 1 combined object. So we've got m1v1 plus m2v2 is going to equal, call this m total, v total for the combined object there. So the mass of our first object is 20 grams. Now we don't want this thing in grams, we want this in kilograms. So I'm going to convert it up here. Divided by 1,000, we're going to get 0.02 kilograms. So we're going to get 0.02 times 100 meters per second plus 0, because this object is, the block hanging there is not moving. And that's going to equal our total object, which is going to have a mass of the bullet plus the block. Now the bullet was 0.02, the block is 4, so this is going to be 4.02. And we want to know what that total velocity is. That's the only thing we don't know. And why do we want to know that? Well, we want to know that because the velocity that this thing launches off at, this v final at this point here, in the momentum part of the problem, v final, is going to equal the initial velocity for the energy part of the problem. So let's finish this off. We're going to get that Vt equals 0.02 times 100 divided by 4.02 is going to equal 0.5 meters per second. That's kind of cool. So now we're going to take this and we're going to look at energy. So we've got initial energy plus work equals energy final. And so now we're totally ignoring this part of the problem. We're saying, okay, if this block and bullet combo are moving with a velocity of 0.5 meter per second, how high are they going to go? So energy initial, this thing, let's assume, to make this problem nice and easy, that this is height 0. So there is no potential energy in this problem. So we're going to get, or there's no potential energy to start, rather. So we're going to get the kinetic energy plus work done equals energy final, and when it rises, it has a velocity of 0. So then over here, all we're going to have is, as it's lifting, it's going to have some potential energy. Now, in this part of the problem, it's important to recognize that work is 0. Because any work that was done happened over here when this thing was embedding itself in the heat and the sound, and it was generated here. At this point, there is no energy lost to any work being done. So we're saying here, energy loss already happened. We can ignore the air resistance. This block isn't moving nearly fast enough for us to consider that. So the kinetic energy here, we're going to have 1/2 mv squared, and that's going to equal mgh. Now, I've got two terms here. There's a mass in both of them, so I can cancel that out because there's nothing weird going on here. I can divide both sides by m, and they're going to cancel. So I'm going to get 1/2. The initial velocity was 0.5, so 1/2 0.5 squared is going to equal 9.8 h, which is going to give us a height of 0.013. Now that's meters. So just to give you kind of a picture of what that is, divide that by 100, we're going to have this thing rise 1.3 centimeters. So the block's not going to lift very far, but it's going to swing a little bit. So the picture that is actually given to us is very over-exaggerated just for the sake of giving you the problem. So that's how we use energy and momentum to combine to look at some of these slightly more complex problems. We're going to do 2 more examples, and that's going to be it. So here we go. A 5 kilogram mass initially at rest slides down a frictionless ramp. Okay, so here we go. We've got a 5 kilogram mass initially at rest. So here we go. 5 kilograms VI equals 0. Slides down a frictionless ramp, which means for this part of the problem, work equals 0. There is no friction. It collides with a stationary 3 kilogram mass. So here is a 3 kilogram mass, and the 5 is going to hit it. And the masses then move apart at different speeds. So we're going to have the 5 moving with some V final, and the 3 moving with some V final. And we want to figure out how exactly we're going to deal with this. Well, this problem is very similar to the last one. Being able to identify how to break these things up is important. The collision happens here. So collision kinds of problems are dealt with using momentum. And falling, turning into some speed, is an energy part of the problem. And they're going to connect here because the final energy for the 5 kilogram block is going to equal the initial energy for the 5 kilogram block in the collision part of the problem. So I'm not going to do all of the work. I'm going to do almost all of it. So here we go. We're going to have half. There's kinetic energy plus work equals. Oh, I lied. Oh boy, that's bad. Sorry. Let's just start that over. We're going to have potential energy to start because there is no. There's no velocity here. There's only potential energy to start. There's frictionless, so there's no work done. And it's turning all into kinetic energy as it drops. So PE equals KE. So we're going to get mgh equals 1/2 mv squared. My masses are going to cancel because there's one term on each side. Both have m in it. So we're going to get V equals the square root of 2gh. Now, I don't have any values here other than, well, the masses, which cancel. I don't know how far this thing's dropping. This is just purely conceptual. This thing's dropping. Velocity is changing like this. And then over here, we're going to get a collision. So we're going to have momentum initial equals momentum final. I have two objects, I'll say m5 v5 plus m3 v3. The 5 kilogram block and the 3 kilogram block equals m5 final m5 v5 final plus m3 v3 final. This block was initially at rest, so this is 0. This final velocity goes there. Now, we don't have any more information to finish the part of the problem. The whole goal of this example was to show you how we would split this thing up. And this is how it would be split up. We would need one more piece of information to be able to finish this. We would need to know either the speed of the 5 or the speed of the 3. We couldn't or we would have to know that they stick together, which we aren't told. So there's no actual way to finish this problem, but this is how this thing would be split up. Same thing with this guy down here, this example 3. Question is, how do we actually split this thing up? Well, what's going on here? We're told that, or based on the picture, we've got M1 connecting with M2. It's going to kick this guy up here. Do they stick? I don't know. Oh, actually, we do know. There are hit and stick collisions. So then M1 and M2 are going to rise up here, stick to 3, and then it's going to keep going. We want to know what the final velocity of this whole conglomeration is. And the question is, how do we split up energy and momentum kind of each step of the way? This guy here, oh, there's a collision here, which makes this momentum. This is initial. This would be final, M1, M2. Momentum initial equals momentum final. Now, this part of the problem is going to be energy. We use the final velocity from the momentum part of the question to become the initial velocity for the energy part of the question. So V final here equals V initial for energy. They're going to rise. We're gaining potential energy. So this is energy initial plus work equals energy final. Over here we've got potential energy because this thing rose, and we're going to assume that it's still moving because it has to connect with that 3. And then this part of the problem over here is going to become momentum. Well, why is it momentum? It's momentum because 1 and 2 hit 3, stick, and then slide over here. So then the final velocity here in the kinetic energy part of the problem is going to become the initial velocity here when these things slide and stick. And then we're not given any more information other than what we see here, because it's not about, I mean, the math is should be relatively easy to do. The whole point of this example is just to look at how we step through the different concepts. So that's it. That's as far as I'm going to take this. The lesson is short because the questions are many. So I want you to look at the following questions for the homework for this chunk. I want you to look at 1. I want you to look at 2. Oops, sorry. I'll move that down here a little bit. I want you to look at 4, which is great. 4 is a solid question. Let's just slide down and look at 4. We've got, oh boy, this is so good. We've got energy over here. We've got momentum over here. And then we've got projectile motion over here. It's good questions. 4 is great. I want you guys to look at 6 as well. I like 7. I like oh boy. The last one I'm going to give you guys to do is 11. I'll make it actually a little bit shorter than the question assignment I posted. So 1, 2, 4, 6, 7, and 11 is what I want you to look at. And then after this, it's review of the chapter.